You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast, and I have a returning favorite guest, Ethan Siegel. He's an astrophysicist, and we're going to be talking about the recent picture of a black hole, which he'll more clearly identify and specifically identify. But that's what we'll be talking about, because I've seen pictures of it in the news, and there's a little bit said about it, but I want to get some more detail. So, Ethan, thanks for being here.
Oh, it's my pleasure. It's so rare that we get a revolutionary discovery like this, where literally nothing is going to be the same in physics after this. And this is such a critical moment. I would put it right up there with the discovery of the Higgs boson and the first detection of gravitational waves as our biggest finds of the entire decade.
Really? Well, it's funny. Most people in the news, I'm sure they saw it and they said, okay, it looks cool. It's a picture. But then they thought no more about it. So why is this so significant?
Well, you have to realize whenever you have a new way to test a scientific theory, or you get to test it in a new regime or to a new precision, that is a test you absolutely are compelled to do. A lot of people have this misconception that the way science works is you have a hypothesis and you try and prove the hypothesis. And it actually works exactly the opposite of that. You have a hypothesis or an idea or a way things might work, and your goal is to test it, not to try and prove it, but to do everything you can to try and disprove it, to try and scrutinize it, to try and subject it to the most stringent tests you can possibly come up with. And there's possibly no theory that's been more scrutinized in exactly this way than Einstein's general relativity. There are all sorts of alternatives to Einstein's relativity out there that have fallen by the wayside because of all the different ways we've managed to test Einstein's theory and all the different ways we've managed to test our law of gravity. Well, when you talk about black holes, you're talking about something that was predicted by Einstein's theory, but was predicted to be significantly different than black holes in any other theory of gravity. General relativity said, okay, we're going to have a collapsed object where all the mass is collected into a small area, and here's the size of its event horizon, and here's what its shape will look like, and here's what we expect the photons, the light coming from outside the black hole, to do when it bends around the black hole and comes to our eyes. So what we were able to do in actually imaging a black hole for the first time, not only is this the highest resolution image we've ever been able to construct in astronomy or any branch of how we look at the universe, this was able to confirm general relativity in a way that we've never been able to test it before. And that for me is the biggest thing of all, that we know this is a black hole and not a wormhole. We know there's a real event horizon here and not a naked singularity. We know that the event horizon isn't a hard surface. And we know that it's consistent with Einstein's picture of general relativity and not many of the alternatives. And that's just like the first straightforward, wow, isn't this an amazing image? You look at that image and all of that information comes right out of it.
All right, well, was Einstein the first person to figure out that there were such things as black holes or the possibilities of them, or was it someone else?
Although it comes out of Einstein's theory, there's actually two parts to that answer. One is that way back when Newton's theory of gravity was our theory of gravity, there was a guy back in the 18th century named John Michell. He was the first to actually theorize that there should be objects that behave the way black holes behave. The way he looked at it was kind of interesting. He said, here's our sun, and imagine our sun the way it is. Now imagine the sun having the same density that it has, except it were bigger, that it had more mass and were bigger, but we kept the density the same. And he noted, as you calculated this, that as you increase the size of this hypothetical sun, keeping it at the same density, the escape velocity, or the speed at which you'd need to travel to gravitationally escape from its surface, would go up and up and up as you increased the size of the sun. And if you got all the way up to about 500 times as large as it presently is, he said, you would have an object where the escape velocity was the speed of light or greater. And although he didn't call it a black hole, he described an object that would be what we would know today as indistinguishable from a black hole. Now, Mitchell was not particularly influential in that regard, but he was a legitimate scientist, and his most famous student, Henry Cavendish, was the person who first figured out how to determine what is the gravitational constant of the universe through the Cavendish experiment using a torsion balance. So that came along, I think, way back in the 1780s. But it was actually someone else who discovered, using Einstein's relativity, that black holes should come out of that theory too. That person was named Carl Schwarzschild, and he was actually a soldier in World War I, where, as soldiers do, they sort of pass around all the information that comes in. And one of the pieces of information that came in was, this guy Einstein published a new theory of gravity, and Schwarzschild read it and said, that's interesting. And on the front lines in World War II, he wrote a paper calculating, hey, you know what? If you had a point mass, here's the solution to it. That's the Schwarzschild solution, and it provides the first predictions for here's what the metric, the description of space-time looks like if you have a black hole. So it was actually Schwarzschild who theorized it, even though this was a couple of months after Einstein first published his theory.
So what were some of the assumptions about what the black hole would look like before the picture was finalized?
Well, so one of the things that you would expect is that when you have a black hole, Schwarzschild said, let's assume it's spherically symmetric, which means it isn't going to rotate. Now, in theory, all astrophysical objects rotate, and because we have a law called the conservation of angular momentum, we would expect that whatever makes a black hole has to be rotating too. So one of the predictions is that this wouldn't be a Schwarzschild black hole, where the solution was discovered for that a few months after Einstein's relativity was first put out, but it should be a rotating black hole. It should be what we call a Kerr black hole. And whereas Schwarzschild's been dead for over 100 years, Kerr, the person who discovered the solution to a rotating black hole, Roy Kerr is still alive. He discovered this solution back in the 1960s, but this was something that, we had to calculate explicitly to say, wow, you know what? We need to have a rotating black hole. There should be a rotation axis that could point in any direction. And when we look at the radio emissions coming from the event horizon and the large-scale jet that we see coming from the black hole and the extended radio emissions that have already been measured by other observatories, the Event Horizon Telescope collaboration was able to tell, you know what, this must be a Kerr black hole. And also, we can determine what direction is its rotation axis pointing in and how fast is it rotating. And the answer is that the black hole is rotating. The rotation axis points away from Earth at about 17 degrees, and it's rotating close to, at about 90% of the limit of how fast a black hole is allowed to rotate by the laws of relativity.
Huh. Interesting.
All of that from the first image. We were also able to see so many other things. You know, a lot of people look at this image and they say to themselves, oh, this shouldn't be. I thought you shouldn't be able to see anything escape from a black hole. How can we see all of this light? And the answer is that actually all of this light is being emitted by matter that's accelerating outside of the black hole. This is matter that is part of an accretion flow around the black hole. Black holes are not like most people, I think, picture black holes as these like vacuum cleaners in space that suck everything in. And black holes don't quite work like that. They do gravitate, but they don't suck anything in any more strongly than, say, our sun, if you were to, say, make our sun the same mass as a black hole would. Black holes are very, very messy eaters. They are more like Cookie Monsters. If you imagine a black hole like Cookie Monster's mouth, where, you know, you could see like cookie after cookie after cookie goes into it, and it gets gobbled up and, you know, maybe even atomized into these little bits, but almost all of these cookie bits fly out of his mouth instead of actually going down his, you know, Cookie Monster throat. That's sort of what a black hole is actually like, is almost all of this matter gets funneled around the black hole. Because it's such a strong source of gravity, it makes matter accelerate. And because you have accelerating matter at these high temperatures, because when matter collides, it heats up, it's going to split apart into the positively charged nuclei and the negatively charged electrons. Well, whenever you have charged particles that move around really fast, they create electric currents and magnetic fields. And it's those magnetic fields that accelerate this matter and cause it both to emit light and get collimated into these jets. So we knew from the previous radio waves and X-rays and optical observations that this galaxy and the black hole at the center of it had a jet. What we were able to definitively determine by constructing this image with the Event Horizon Telescope is that there is matter. There really is matter around this black hole, and that is consistent with what we thought should be happening from accretion disks and accretion flows. In order to explain the radio results, you need these accretion flows, and they also predict that you will get other emissions that don't show up in the radio, like X-ray emissions. And so, lo and behold, when we look with the Chandra X-ray telescope, we see these X-ray emissions. We see with the Event Horizon telescopes that the accretion flows get hot. And this confirms the picture that what we have is electrons moving close to the speed of light and accelerating due to a magnetic field.
So the material that accretes, it goes into a circular orbit around the black hole, or is it spun outwards or spun inwards, or what happens to the material around it, and how long does it stay there? Where does it go?
So what we can see, and this is not just from this particular black hole, but this is maybe even more pronounced from the black holes we find in our own galaxy because they're lower in mass, is black holes actually change in their emissions over time. A lot of people weren't expecting the black hole at the center of this galaxy M87 to be the first one that they built an image out of. A lot of people were expecting it to be the black hole at the center of our galaxy. But I think there's a very important reason why this other black hole was chosen rather than the one in our galaxy. And that's because when you talk about a black hole, you're saying, okay, well, I'm looking at it at a particular moment in time, and I expect its features to actually change over time. How much time should it take for those features to change? That's actually going to depend on how much time it takes light to go from one side of the black hole to the other. It's as though you had a light travel time that you were measuring how fast a photon travels from one side of the black hole to the other. Well, if your black hole is large and supermassive, like way, way bigger in mass, the bigger in mass it is, the larger its event horizon is, and the longer it takes light to travel from one side to the other. This very first image of the event horizon of a black hole is actually made of 4 separate images. There were images taken on April 5th, April 6th, April 10th, and April 11th. And this is fascinating because if you look at the mass of this black hole and say, what should the light travel time across this black hole be? The answer is around a day. It should take around a day for light to go from one end of the black hole to the other. If you look at the April 5th image and the April 6th image, they're almost identical. There are only slight changes. But if you then go and look at the April 10th image and the April 11th image, they're almost the same as each other, but they're different from the April 5th and April 6th image. You can see the black hole is starting to vary, and this is because this is how long it takes the matter that's on the outskirts of the black hole, that's falling into the black hole, to change its configuration. This is great for making an image because it means you can take like a day's worth of observations and the black hole doesn't change all that much over a day. So you can take a days of observations, add them all together, and get a result for, here's what the black hole looks like. If you're looking at the black hole at the center of our galaxy, the one at the center of the Milky Way is an estimated 1,500 times less massive than the one at the center of M87. So for that black hole, instead of something that varies on the time scale of a day, you're talking about something that varies on the time scale of about a minute. So we see our galaxy's black hole, we see it flare, and we see the flares turn off, and we see it have a spike in X-ray emissions, and the spike goes away. And for black holes that are even lower in mass, for these stellar mass black holes that we find in our galaxy, we have started to call some of those micro quasars because they start showing these big variations on time scales of less than a second, because that's how long it takes matter to fall in. So when you're asking, how long do these accretion disks last? How long do these accretion flows last? All of that is dependent more than anything else on the actual size of the black hole we're looking at.
Okay. Why is does the center of it appear black? I would think that some light that just happens to be between us and the black hole that gets spun off from the black hole would come to us and we'd be able to observe it. So maybe it's a stupid question, but why is the whole center black? Why is the circle black?
Well, there's not. This is not a stupid question at all. So if you were to say, look exactly at the black hole, and you could somehow see the event horizon itself, you could see that region from which nothing, not even light, can escape, it would actually be significantly smaller than the interior radius of that dark spot we see on that ring. That dark spot is actually bigger than the event horizon itself. What we're seeing is what I would call a photon ring. There is a path that photons take when they're emitted in the vicinity of a black hole. They get bent because the curvature of space is very severe. So any photon you make or generate or emit or that comes off of the matter is going to get bent around the black hole. Now, if you're observing this black hole from anywhere, what you're going to see is all of those different light paths that get bent around the black hole and wind up going off in the direction right along your line of sight. So you're seeing a bunch of photons, a bunch of light rays that come out parallel to each other and that draw a line from the center of the black hole or near the center of the black hole to your eye. So what you're seeing is the gravitational bending of light by the event horizon. What we see as the shadow is that region where all of those light rays that would otherwise come to your eye Instead of coming directly to your eye, they actually get sucked into the black hole instead. The photons that are captured cause that dark shadow that you see, and the photons that aren't captured, they create that characteristic ring that the Event Horizon Telescope so beautifully observed.
So since this is rotating, wouldn't its gravitational shape change? Wouldn't the event horizon be morphing and moving and changing? Wouldn't the curvature of space around it be constantly changing and modulating?
Well, it's not that it's constantly changing, because it's not like the rotation axis is changing. We don't think this black hole is precessing the way that, say, a spinning top precesses, where the rotation axis changes significantly over time. It may do that for smaller black holes, but for a really big black hole like this one, we haven't seen any evidence of that. What you can do instead, though, is say, well, if the black hole is rotating, what should that mean? And it should mean that what happens is one part of that ring, of this photon ring that we see, one side of it should be brighter than the other, and that there should be extended emissions in some directions and not others. And from reconstructing both the brightness of the ring, where the bright spots are, where the bright spots aren't, where the dim spots are, where the dim spots aren't, and what the off-axis, outside of that ring, if you look really closely, you can see that there's the beginning of extended emissions. That's what we expect to be asymmetrical, and that's the information where that's all encoded that we can use to say, oh, here's what that rotational information should be. Here's what that rotational information should reveal to us.
So what do you think the curvature of space-time is at one point or on one side of the black hole versus the other? The leading side where the rotation is going towards versus the other side. What would it look like, I guess, radially around it?
If you were falling into it, that's what's really going to change. Is it depends on what direction you're moving relative to this rotation, because what's actually happening is that space itself is being dragged, and if you go inside the event horizon, the reason you can't escape from the event horizon is that space itself is actually being dragged faster than the speed of light inside the event horizon. Remember, when we talk about special relativity and that idea that nothing can move faster than the speed of light, what we're talking about is that nothing can move through the fabric of space faster than the speed of light. But there's no restriction on how fast space itself can move. So when we're seeing, what's going on to this matter that's getting accelerated? Well, it's emitting radiation. And when you say, well, one of these sides is coming towards you and one of these sides is coming away from you, what does that mean? The biggest thing that it means is we expect to see a difference in the temperature of the radiation we're seeing. If you're looking at the temperature of the brightest part of the photons coming from around the event horizon, we believe that the effective temperature there is somewhere around 5 to 6 billion Kelvin. 5 to 6 billion degrees is what that matter around the event horizon is being heated to on the leading side. But if we look at the trailing side, the side that's moving away from us, it's only about half that. The temperature gets effectively just about halved by the fact that the part that's rotating away from you is not getting as hot with respect to you. But if you were the one that fell in, everything would fry you pretty much equally.
So there's no void being created by space being pulled or stretched, I guess, as you enter the event horizon. There's no void left behind?
Well, when you're talking about a void, I should maybe ask you to be a little more specific, because to me, void can mean a lot of things. And although it's true that there's this region where nothing, not even light, can escape, it's not like this is a region that's doing anything other than, we draw a boundary around it, because if anything goes inside of it, it gets sucked towards the central singularity. And if anything, escapes from it, then we know it never crossed into that region.
Right, but if you look at, right at the boundary, outside of the boundary, there's, I don't even know what it is, but there's the fabric of space, which is, I guess, mostly vacuum. There's a little bit there. But then does that get pulled into the event horizon, or does it just, I mean, what happens at the interface? What happens with, like, the fabric of space-time? It's hard to even, give it words, I guess.
Well, so if you're thinking about the fabric of space-time, we can actually talk about what's going on outside the event horizon, in the event horizon, and then on that last part, we can talk about what's going on. You're basically saying, okay, you've got a black hole. You're telling me it's spinning. So what's going on inside of it? And the answer is that, we can say, okay, here's what we have. We have a rotating black hole. So there's actually, instead of one event horizon where you say, okay, if I said I'm going to solve these equations and ask where is the event horizon for Schwarzschild black holes, for the totally spherical case, you get an answer and it says the event horizon is right here. Well, instead of a single solution for where the event horizon is, a rotating black hole has two mathematical solutions, what we call an outer event horizon and an inner event horizon. So mathematically, there are two solutions to where the event horizon should be. What we saw when we looked with the Event Horizon Telescope and we took this image, we kind of knew what the mass of this black hole should have been already, because we had a couple of different ways of inferring what should its mass be. One was from X-ray data, and the other was from the gravitational data of the matter that falls into it. Well, we found a black hole that was consistent with the prediction of the outer event horizon, not the inner event horizon. And this, to me, is brilliant, because it said, a lot of times in mathematics, we get multiple possible answers. Like if I said to you, hey, Rich, I have the square root of 4 oranges, you would say, oh, that means you have 2 oranges. And I would say, well, how do you know? How do you know I don't have negative 2 oranges? And you would say, oh, well, negative 2 is also the square root of 4, but I know that if you have a physical number of oranges, it has to be a positive number. You can't have negative 2 oranges. It's not like you could have negative $2 billion. It doesn't work the same way money does. It works like the way oranges work, where you can either have them or not have them, but you can't have negative of them.
Right.
Well, we didn't really know how this would work. So first off, if you're rotating, you have two mathematical solutions, an inner and an outer event horizon. Well, outer event horizon is the one that's physically real and physically meaningful. But we also know a few extra things that are really cool. One is that outside of even the outer event horizon, there's a place known as the Ergo Sphere. And this is the name we give to a place where space itself is dragged around at a rotational speed equal to the speed of light. And particles that fall in there will experience enormous accelerations. They can still escape from the pull of the black hole itself. That outer Ergo Sphere is someplace where if a particle gets the right acceleration and is traveling in this super accelerated space, it can still get kicked out of the black hole. So we expect there should be some matter that falls in there that passes through that surface, that if we can get the resolution to be even greater on the Event Horizon Telescope, maybe we can start to see where those photons are being emitted from and map out that ergo surface or that ergo sphere. We also know that there's a maximum ratio of angular momentum to mass that's allowed. You know what gravitational waves are. You know that gravitational waves carry energy. from any object at all. Well, if you have a black hole that rotates too fast for its mass, if it has too much angular momentum, that black hole is going to radiate that extra rotational energy away via gravitational radiation until it's below that limit. Now, I told you that this black hole was already at about 90% of that limit. It makes me wonder if when we first form black holes, or when two black holes merge to form an even more massive black hole, maybe sometimes we go over that limit, and we need these black holes to radiate that gravitational energy away. And when they do, maybe we'll even have a chance to detect them. That could be a future project for either LIGO or one of the space-based gravitational wave observatories like LISA down the road. And one of the coolest things that I just have to mention is that when we say the word singularity, we almost always think of a point. We think about, like I've got one point down here at the center, and that's what everything falls towards. Well, if your black hole is rotating, that singularity is not a point, but rather it's a one-dimensional ring, where the radius of that ring is determined by the mass and angular momentum of the black hole. For this black hole at the center of Messier 87, if we were to calculate how big would that ring be, it would actually be about twice as big as Pluto's orbit.
Oh, wow, it's huge.
That's pretty huge.
How far away is the closest black hole to us that we've been able to figure out?
This is not something that's very well known, because when we say the closest black hole, the way we detect black holes is because they have to be in binary systems. Unless you're a supermassive one at the center of a galaxy, the other type of black hole that exists is a stellar mass black hole. But black holes themselves don't emit any radiation, so we can really only detect them if there's another star orbiting that black hole, right? So if that star orbits the black hole, it will accelerate in particular ways, it will emit X-rays, and when we see those X-rays, we can start learning some things about the black hole. Well, the first one we ever found was back in the 70s, and it was called Cygnus X1. And this was the first X-ray source that was widely accepted to be a black hole. But there's a closer one. Cygnus X1 is about 6,000 light years away. But there's a closer one that's only about 3,000 light years away, and it is a star called V616 Monocerotis. And you will say, that's a mouthful. Well, you might have seen something about this because it's a variable star and it's undergone a couple of X-ray outbursts. The first one was in 1917. The second one was in 1975. Now we know these are X-ray novas. And so you can say, wow, here's this object, and what we think it is we have a main sequence star that's a little less massive than the sun. There's also a second object there that has a mass of about 6 or 7 solar masses. It emits no light. It's too massive to be a neutron star, and therefore it has to be a black hole. It's about 3,300 light years away, and that is the nearest known black hole to the solar system. These two objects, the star and the black hole, they orbit around each other once every 8 hours. So 3 times a day, these objects complete a revolution around each other. It takes a system that close and that extreme for us to be able to detect it. So even though I'd say 3,300 light years is the closest one we know of for sure, I'd definitely be willing to bet that, there are probably black holes that are even closer to Earth. They just haven't found them yet.
I guess I imagine the black hole's sitting there at some point in space, rotating or not rotating, but you said they're moving through space?
Well, everything moves through space. If you're in the galaxy or if you're in the universe, you're going to move through space relative to all the other objects. They have mass. which means they have to orbit gravitationally around the galaxies, and that the other masses around them are going to gravitationally pull on them just as they pull on the other masses in the universe.
So what's in front of a black hole, I guess I'm just going to put it in those terms, what's in front of it, eventually the black hole moves through that part of space, but what's behind it? As a black hole moves or orbits, what's left, quote unquote, behind? How does it affect space that it's moved through and is no longer there?
Well, remember, a black hole is really not that different from any other source of matter you have. So if I were to replace that black hole with a star of the same mass, it's only that innermost region that would be different. So anything that, if you had a star, stars are much, much bigger than black holes are. Our sun, if you were to compress our sun down to be a black hole, right now our sun is 1.4 million kilometers in diameter. If you were to shrink the sun down to be a black hole, it would be about 6 kilometers in diameter. So when you're saying, okay, like, what happens to the space in front of a black hole when it's moving or behind the black hole? Well, the answer is, not a whole lot, unless there's something in it. Because even though that space will distort as the black hole approaches it, passes through it, and then passes beyond it, that space that it was once occupying goes ahead and it undistorts behind it. So these are what's happening. Is the fabric of space is not some fixed thing that never changes. As the matter in your universe changes in distribution and rotates and does all the things it does, the fabric of space is going to change in response. There was a famous scientist called John Wheeler, and he just put Einstein's relativity in the simplest terms I've ever heard, and I use it all the time now. He said, matter tells space how to curve, and curved space tells matter how to move. And that's the simplest explanation of general relativity I've ever heard, and it's absolutely right. So what it's saying is, if you have matter like a black hole that moves through space, it's going to curve and distort that space and change its curvature as the matter moves through space. But that changing curvature of space is also going to change how matter and light and anything with energy responds and moves through that curved space. So specifically, if you're saying, okay, I have a black hole, I have matter in front of it, I have matter behind it, and the black hole's moving through space. Well, as the black hole approaches the matter, what's going to happen is that matter will get distorted and accelerated and likely torn apart into streams, and some of those particles that make up that matter are going to get sucked into the black hole, and some of those particles are going to get accelerated into an accretion disk or an accretion flow, and other particles are going to get ejected entirely. They'll get accelerated in one of two jets on either side of the black hole. Meanwhile, things behind the black hole, if the black hole is moving away from you, same thing. Some of the matter will get sucked in, but some of the matter will get ejected. So it's really just a question of what is your, gravitational potential energy relative to your kinetic energy. If you fall in, then you fall in. If you don't fall in, you probably get accelerated and ejected. And that's really what we're looking at. That's really how these objects, these black holes, are working. A lot of people, by the way, were expecting that maybe as this matter goes around the black hole, we should be able to see some of it crossing in front of where the event horizon is. And although we didn't see that for Messier 87's black hole, we're not entirely sure why. We're not entirely sure if this is because, it's just oriented in a particular way, and that's not what we're seeing, or if the answer is actually there is matter being accelerated in front of that event horizon along our line of sight, similar to the black hole you saw in Interstellar. And maybe we just need to achieve higher resolutions and greater sensitivities to tease that feature out. A lot of people, including me, weren't really aware of it at the time, but the very first simulation of what a black hole's event horizon should look like was made way back in the 1970s by Jean-Pierre Luminet, a French scientist. And what he determined was exactly what you might be thinking of. He even had that little, the ring around the black hole, but then a place where it crossed over in front of it and obscured some of it. Now, we didn't reveal that for this black hole, but it's possible that it's really actually there, and with better imaging, we'll actually be able to reveal it.
I just have one more question about the fabric of space. So, again, what's left behind once a black hole moves through space? You said, the space warps and then it unwarps. But what does that tell you, that something so dense and so, gravitationally strong can pass through space, and once it passes through and moves on, space seems to go back to the way it was, untouched, untorn, undamaged? Does that tell us anything about,
What it tells you is that our idea of space, that it's a fabric, that it doesn't get torn apart. The big thing that it teaches you is that space stays continuous. It doesn't get broken and remain broken, even in the presence of a singularity. So there are a lot of things that we don't understand about singularities at all. Someone once tongue-in-cheek said that singularities are where God divided by zero. And I've always liked that because, as anyone familiar with math knows, dividing by zero is the quickest way to get nonsense answers out of anything you do. But what this tells you, what that fact tells you, that space is not destroyed and there is not a wake of destruction left behind, a moving black hole, this tells you that whatever a singularity does is it's not destructive to the fabric of space itself. Even though we don't know what's going on there, do know that space remains intact. That once you're outside of a black hole's event horizon, even if a singularity went and passed through a certain region of space, that space remains intact with all of the properties that Einstein's relativity says it should have.
Yeah, I figured it would tell you something. That's why I was thinking about that. Interesting. So,
yeah, it's fascinating stuff. And what I think is also fascinating is that there were a large number of things that we still get to learn. Right now, the Event Horizon Telescope only has the resolving power to see 3 black holes, the one at the center of our galaxy, the one at the center of Messier 87, and the center of another galaxy called NGC 1277. But people are already planning on going beyond what the Event Horizon Telescope can do today. We're limited in what the Event Horizon Telescope can see by the size of the Earth. We have telescopes and telescope arrays all over Earth, and that's what we're seeing. We are at the resolving limit for what an array of radio telescopes with an effective diameter the size of the Earth can see. But we already have a mission called Radio Astron in space, where we have a radio telescope in space networked with telescopes here on Earth. If we sent an array of radio telescopes in orbit around Earth, we could get much, much greater resolution to what we have today. If we increased the baseline, which means the distance between telescopes, by a factor of 10 or 100, our resolution would increase by the same amount, which means instead of just 2 or 3 black holes, we could reveal hundreds of them or maybe even more, which is really, really phenomenal. We're going to see possibly the presence of additional black holes near the center of galaxies. We're going to maybe find our first supermassive black holes that aren't associated with galactic centers. And what's even possibly more exciting is that all of this data we have, these are just these are just radio images that we have, but we're also getting polarization data, because light is not just, you have this photon come in. It has electric and magnetic fields, and the way those fields are oriented will tell you something about the polarization of this light. That will enable us to reconstruct the magnetic field of a black hole, which will give us an entirely different view of this object.
So yeah, why? Maybe it's not obvious, but why is this picture so historic? How is this going to change how physics is done and how black holes are observed?
Well, up until this, we had never seen an event horizon before, which means we didn't even know if event horizons and black holes, as general relativity predicted them, exist. Now we do know that. And when you're talking about what else can we learn, what else is going to come from this, well, some of the things we've already learned is there are two ways we have of estimating the masses of black holes. One of them came from looking at the gas around a black hole. For Messier 87, that gave an estimated mass of 3.5 billion suns. On the other hand, there were gravitational estimates, where you could have individual stars orbiting a black hole or the absorption lines from stars orbiting a more distant black hole. For Messier 87, that gave an estimate of 6.2 to 6.6 billion solar masses. There's a big difference between 3.5 and 6.6. Well, the Event Horizon Telescope told us what's the size of that black hole, which means what's the mass of that black hole. It gave 6.5 billion solar masses, so it's already taught us that gravitational dynamics of stars give good estimates for black hole masses, but observations of gas do not. So there's a chance to learn more astrophysics there. Why are the gas measurements biased? How are they biased? And why do the stars give such good measurements where the gas doesn't? We will learn if black holes all rotate, and if the rapid rate of rotation that we've seen for this one is common or not. We're going to try and learn what is the strength of gravity and gravitational lensing around the black hole. They had expected almost all of the flux from the black hole should come from near the horizon, and that the emission interior to where you expect that horizon to be should be dramatically depressed. And that's exactly what they saw. That's direct evidence for the predicted shadow of a black hole. We're going to be able to see if they change over time. We're going to be able to watch them jitter and infer from that, just like you would from Brownian motion of particles under a microscope. We're going to be able to infer that there are all these small masses around it knocking this big black hole around. We expect that there will be small black holes in orbit around the centers of galaxies whose gravitational effects we can't see individually, but that we should be able to see on average. And maybe most excitingly, I told you earlier that black holes flare. We're going to be able to learn how. What is the physical origin of these black hole flares? Well, M87 is probably not the right black hole to look at, but the one at the center of our galaxy is. That variability on timescales of a minute means this black hole's features are going to evolve quickly. And when a flare happens, we'll be able to look for hot spots. We'll be able to see how do the temperature and luminosity of the radio features change. Are there magnetic reconnection events happening like they do when our sun gives off a coronal mass ejection? Is there an object being sheared apart in the accretion flows? The black hole at the center of our galaxy flares every day pretty much. So we'll be able to track the signals associated with these events. We'll be able to learn what drives them, and maybe we can even learn what is it that's falling into the black hole to make them flare. So as far as we've come, and as remarkable as this first image and the first discovery was, we're really just getting started learning about the physics of these extreme events, these extreme environments, and what's going on with the supermassive black holes in our universe.
Yeah, I just thought you'll learn what makes Cookie Monster burp.
Oh, I should have phrased it that way. So much better. So much better. It was Jim Henson. We're going to find him there.
One last question about, you said the new telescopes will be coming online. I don't know when, but they'll be out in space making the effective diameter of our
This is the hope. These haven't been launched yet, but we hope to be able to build them. The Event Horizon Telescope was kind of a piggyback observation, right? It was something where all of these telescopes already existed. The Event Horizon Telescope team just needed to get permission to go in and network them all together and install new software and hardware like atomic clocks so that you could do time syncing. But this new proposal to say we want an array of radio telescopes in space to network together too, someone else is going to have to build that. Someone's going to have to get funding to build that. And so even though they've got one telescope up there now, you really need an array. You need at least 3 more over what we have to start to construct a 2-dimensional picture of what's actually out there. So this is something that I really hope starts to happen, but it's not yet something that's a sure thing. As with all things, there's a limited budget that people have for things. There's a limited budget that nations and the world has for things. And if we don't choose to invest in saying, we took this amazing, remarkable step, let's take the next one, it could be generations before we actually achieve all of these dreams that I'm so excited for.
Okay. Well, very good. Well, what's the best way for people to find out more from you and to connect with you?
Well, if you want to find out more from me, I'm always easy to find at Starts With a Bang. So my blog is Starts With a Bang on Forbes. I'm Starts With a Bang on Twitter. I have a Facebook page. And if you have a question for Ask Ethan and want a chance to be chosen for my weekly column, you can send an email to startswithabang@gmail.com. And finally, I couldn't do all that I do without the support of everyone who funds me on Patreon. And I'm Starts With a Bang over on Patreon as well, if anyone you like is interested.
All right, that's great. Well, Ethan, thanks for coming. I really appreciate it.
Hey, it's my pleasure, and I'd encourage everyone to keep an eye out on the Event Horizon Telescope, because even though they've released their first image of a black hole, I would absolutely be willing to bet that the next image of the black hole at the center of our galaxy is going to be the next one up. So when we're looking at that one, instead of looking at a black hole that's some 60 million light years away, we're going to be looking at one right here in our own galaxy. The data's already been taken. It's already being analyzed. The Event Horizon Telescope team just needs to figure out how to construct that more difficult, rapidly changing image from the data they already have. Once we have that, we'll finally know what the black hole right in our own backyard looks like.
Wow. All right, very good.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.